At the end, going further to the banquet. And we will start with a talk that is a collaboration between prestigious institutes like Ottawa, Erlangen, and Napoli. And the talk about optical polarization Möbius stripes will be given by Robert Boyd. Robert, please.
Okay, so Cornelia, thank you for the introduction. I thank the organizers for the invitation to be here. Very first thing you should note is that I am not Ibrahim Karimi. The program would indicate he's giving the talk, but his visa did not come through. So, so I'm giving the talk for him. Now, we're not breaking the rules. I will give my own invited talk on Thursday. This is not my invited talk. This is Ibrahim's invited talk. So just think that I am talking to you with an Iranian accent. Okay, so as Cornelia said, this is a collaboration. But I just want you to see this here. This is here both because of Gerd Loix, and the University of Ottawa has just been designated to be a Max Planck Center. So we're very, very pleased that we now have our own Max Planck Center in Ottawa. But I care, maybe you don't, so let me go on. Let me tell you let me show you the pretty picture first. So we have observed an optical polarization Möbius strip. Some of the authors are in the audience here today. This was published in Science earlier this year. This is a pretty picture. The idea is that Möbius strips, we all know about them. I mean, we played with them as children, but how often do you walk down the street and you see one? I mean, for as pervasive as they are in mathematics, it's fairly rare for them to appear spontaneously in nature. So we have found a situation in which Möbius strips actually appear in a physical system, and this is in a tightly focused laser beam. So let me tell you the story. Okay, so this is a standard Möbius strip built out of paper. Isaac Freund proposed a number of years ago that the polarization of a structured laser beam, tightly focused, would spontaneously form a Möbius structure. And here's what we mean. Okay, tightly focused laser beam, I'll tell you the details later. Now draw a circle around the axis of the beam. Plot the major axis of the polarization ellipse as a function of position, and after you go around the circle once, you find that the axis of the ellipse has changed from this to this. Of course, there's nothing physical here. I mean, you don't have to worry about them interfering destructively. It's a mathematical concept. It's the major axis of the polarization ellipse that becomes inverted when you make one loop around the axis. So what did Isaac Freund say? That optical Möbius strips can be found in light fields, but one has to find a very special field distribution and then measure it in a very precise way. So in case I run out of time, our session chairwoman says that she will be unrelenting in keeping me on schedule. So I want to give you the result at the beginning of the talk in case I run out of time. So this is the result, theory and what we measured in the lab, and they are just so similar that from now on I will show you only the measured, not the theory, because they agree so well. So here we form a topological structure with a topological charge of -1/2. Here we find one with a topological charge of -3/2. And as you go around the circle, you can see how many half twists there are. Okay. In Möbius geometries, they're quantized in half twists. So this is 5 half twists, this is 3 half twists as you move around the circle. So the number of half twists is the topological charge, absolute value, plus 1. So how do we form a beam of light that will have this structure? Well, there's something that people in polarization vortices call a lemon type structure. It has this type of polarization structure. This is the very center of the beam. It's circularly polarized, but there's all types of elliptical and linear polarization surrounding the center point. What we do is we take left-hand circular light in an LG00 mode, superimpose it with right-hand circular light in an LG01 mode, and if you just work this out, this is the type of polarization structure you get. So we call this a vector beam because the polarization changes. The polarization is different at different points in the transverse plane. Okay, so how do we make our vector beams? Well, we do it with a Q plate, and I wasn't here this morning, but I think that we had invited talk on Q plates, so you know all about Q plates. But unfortunately, it's part of my talk. You're going to hear it again. Okay, so we use Q plates. Yeah, Lorenzo gave a talk this morning. We use Q plates to form the vector beam. So let's just remember how a Q plate works. Think of it as a non-uniform wave plate. This is a liquid crystal device. The orientation of the director, the major axis of the molecule, changes as a function of the azimuthal angle as you move around this structure. Well, each one acts as a half wave plate, but the orientation angle of the half wave plate changes as a function of azimuth. As a result, if you bring in a Gaussian beam, left-hand polarized, being a wave plate, it turns into right-hand circular polarization. But by conservation momentum, then it has to add 2 units of orbital angular momentum to the beam. If you come in with right-hand circular light, it turns into left-hand circular light and removes 2 units of orbital angular momentum from the beam. So this is the basic way. So in our implementation, this is how we form the vector beams of light. So just to remind you, how would one construct a Q plate? And let's do the example of Q equals 1, Q being the topological charge. So conceptually, go to the store, buy yourself a half wave plate, cut it up into wedge-shaped pieces, and then rearrange the pieces as shown here. So rearrange them as shown here, and this is, well, conceptually, how one builds one of these Q plates. And don't forget, this is Ebrahim, not me talking. And Ebrahim just wants to remind you that this spiral staircase at the Vatican is very much like a helical phased laser beam. Okay, how do they actually fabricate the Q plate? So they take a substrate, they rub it in the azimuthal direction, they put liquid crystal molecules down, the molecules tend to align in the grooves that they have put there. Then they make a sandwich by putting a superstrate on top of it, squish it together, and there is your Q equals 1 Q plate. Now, how did we actually do the measurement? So the claim is that the polarization forms a Möbius structure. So here's how we do it. And this, for this example, this is just any donut-shaped beam of light. We take a nanoparticle, 90 nanometer diameter nanoparticle. We raster scan it through the focal region, and we look at the scattered light. There's light scattered in the forward direction, light scattered in the backward direction. We can put a polarizer in that beam so that we can independently measure the X, Y, and Z, or Z in Canada, polarization components of the scattered light. and it works. So this is just a donut beam, just to show that the technique works. So here, this technique is able to show you the measured intensity distribution. But as I said, you can also measure the polarization and the phase. Oh, so you interfere with a plane wave. So you measure interference fringes. So that's the basic measurement method. Well, it's easier said than done because you have to scatter the light into the far field. You make the measurement in the far field. And then, knowing the Fresnel propagator, you have to infer back to what the field distribution was like at the nanoparticle that did this. The Loix group has spent, I think, literally years learning how to do this. So it was fortuitous, well, for me, that all the hard work had been done already. Then we just came in and did a splashy experiment. So here's how the experiment actually works. Laser beam comes in. You put the Q plate here. You put a Fourier filter. It's a pinhole. You put just to restrict the scattering angle. Microscope objective 0.9 numerical aperture. I haven't mentioned this already. The reason why you have to focus so tightly is that you want there to be a three-dimensional distribution of electric field vector. Right? It almost doesn't make sense to talk about a Möbius strip in a two-dimensional space. You just don't know what that means. So you have to have a structure embedded in a three-dimensional space for it to even make sense to talk about a Möbius structure. Here's that nanoparticle that we raster scan through the focal region, piezo stages and whatnot. Here we show it for collection in the forward direction. Now, trick, what do we put, what actually do we put on this Q plate? So I didn't mention this. A Q plate can be controlled with a voltage, just like any liquid crystal display. So as you change the voltage, you would change the extent to which the molecules become aligned. So you can change the retardation of the wave plate. If there's no voltage, the retardation is 0. This just becomes it just lets the beam go through. You get an LG00 left-hand circular. If you would adjust this to pi radians, it then becomes a half-wave plate and converts the left-hand circular to right-hand circular and changes the orbital angular momentum quantum number. But if you set this for pi equals 2, then you get the linear superposition of the Gaussian beam and the LG01, and that allows us to produce a star, a so-called star type of vector beam. So this is what we actually did in the experiment. And okay, so this is what the data looks like after collection. So I guess I lied. I do show both theory and what we measured. What we measured, we really call reconstructed because there's a iterative mathematical procedure. It's not what we measured. We measured in the far field and then inferred back. Very good agreement. This is for Q equals -0.5. This is the total intensity, the intensity in the X, Y, and the Z components. Intensity plotted here, phase distribution here. And okay, so that's what the raw data looks like. And I guess I showed you this already, but when I showed it to you before, I didn't tell you how we had gone about doing the experiment to collect the data. So here it is again. For Q equals -0.5, we get a Möbius structure of this form. for -3 halves, we get a Möbius structure of this form here. So here are some conclusions. So what have we accomplished? Well, we have demonstrated the generation of an optical polarization Möbius strip in tightly focused light beams. But so what? We can brag about this. Is there anything deeper than the fact that we built a Möbius beam that nobody really cares about? Well, of course, some people care about it because there are other people who are doing this. But I mean, the general population probably doesn't care about this. So, but is there some significance here? Well, I think one is that these results show that focused light fields can possess pronounced subwavelength features. And if you were trained in, if you know about Gaussian laser beams, you say, well, it's a Gaussian here, and it's a Gaussian in the focal plane. What's the big deal? But I think our community realizes that there are pronounced sub-wavelength structures in the focal region of a tightly focused laser beam. And also, perhaps most significant, is that we've developed, especially the Loix group, has developed laboratory procedures that can be used to probe this sub-wavelength structure of these laser beams. So again, now I'm Ebrahim, I'm not Bob. So this is Ebrahim's group at the University of Ottawa. You see, I'm still an honorary member of his group, so I appear there. But here's Ebrahim with his students, and I guess, roughly speaking, in order of tallest to shortest. So that's his group. Now, here are the enormous number of people with whom Ebrahim is collaborating. And if you're lucky, you'll see your picture there. And finally, Ebrahim especially wanted me to tell you that he is organizing an international workshop on structured light and matter, and it will be held at IASBS, which is in the city of Zhanjiang, if I said it properly. It's just like 2-hour drive north of Tehran in Iran. And it will be September 2016. And here are the confirmed speakers already. And anybody else who's interested should just contact Ebrahim about being part of this meeting. So thank you very much for your attention.
Thank you, Robert. On behalf of Ebrahim, other questions, please?
Yeah, radial vector beams, in focus, have a peculiar distribution that includes a longitudinal component.
Oh, yes.
Have you measured that?
Yeah. Let me go back. Yeah, so I mean, here it is. This is the longitudinal component. So we did measure the longitudinal component of the light in the focal region. And again, numerical aperture 0.8.
You do it for the radial one where
Oh.
all the orientations are radial. Yes.
Well, I assume we have, yeah. Garrett, you've done that, yes?
Yeah, so the
So much of this work was done in airlining. Let them answer.
The direction in which the electric field points goes sometimes, goes in all X, Y, and Z direction. This is what Bob said. To confirm the smoothness band, you need all 3 directions. Otherwise you wouldn't. But that's a standard thing. Already Richardson and Wolf calculated in 59 the detailed structure even if you just have a linearly polarized light beam back and forth. So maybe you know about this.
Maybe this is the key paper, right? This was the paper in which your group showed how to perform these measurements. And I don't remember exactly everything that's in that paper. Oh, Thomas Bauer. Thomas, okay. That's the famous Thomas Bauer, who was the first author of the science paper that I reported. So you could ask him.
Another question? I don't see any more, so thank you once again. Now we speak with Möbius bands and former
More movies.
Questioner is now the second author of this session. It's
Hello, everybody. Thank you. Thank you for coming. I'm officially in the organizing committee, although I didn't do nearly as much work as Giovanni and all the locals, and I want to thank them all for all the hard work that goes behind the scenes to getting the locale and the food and everything put together for this conference. So I'm going to tell you of our own efforts to measure Mobius loops on polarization. Is there a laser pointer?
It's part of it, yeah. It's part of the
Okay. And okay, and then this was done at Colgate University, and co-authors are John Zielski, Corey Beach, 2 undergraduates, and my colleague Bazat Khashavi, who is finishing his PhD at Colgate. So this work was motivated by the work of Freund that Bob mentioned, and also Mark Dennis published on that recently, and it's just a very intriguing effect, how in 3 dimensions you have that the polarization of light can have such a rich structure. So that was my motivation and just curiosity. And of course we have this recent work by the group with Ibrahim and the connection with Ottawa and Germany and also Italy. And and now, so in that work, the idea is to prepare one of these Poincaré beams and focus it down, and then there's a Mobius structure in the polarization of the light. So our approach is really to basically just across 2 beams, so non-collinear superposition of 2 beams, and from that infer that pattern, which according to Freund exists. And actually, if you do the simulations, they do exist. So I'm going to tell you a little bit about Poincaré beams, the Mobius fields, and the status of our experiments. I can't report on a successful reconstruction, unfortunately. A little bit about line singularities, because this is very relevant. It was originally presented by Barry and Hanai in 1977. Properties of topology, that you have these singularities in lines. This line just ends there, and all the lines just go around it. Or you have this triangle-shaped line. And you can also associate that to a topological feature. And then these lines are the radius of the principal radius of curvature of any particular point on this ellipsoid. And then right at one point here, you have a degenerate point where the radius of curvature is spherical. So there's no particular direction for the major radius of curvature, a principal radius of curvature of the surface. So, so then you could think of these patterns in terms of vectors, and the center point is called the umbilic, and you could think of a vector, and as a vector goes around, it turns. So the direction of the vector turns, the direction of the line turns as you go around a circle. So the center is a singularity, and that's what it's called, the umbilic. And you can also have when the vector turns in the opposite direction. And then there's these lines that have special significance that distinguish lemon and star. And then there's this hybrid, which is a combination, not a combination, but a type of singularity that has properties of lemon and star. And for polarization, you can have, this might not be seen from far away, but you have little ellipses drawn here, And, and these ellipses, you can find these lines going through the, along the directions of the semi-major axes of the ellipses. So you have a lemon pattern here. And now, just to visualize kind of that pattern, we have this false color. So red, it means that the semi-major axis is horizontal. This light blue is vertical, and then diagonal is green, and so on. So then you have the lemon, and then you have the star. You can see that for the lemon, you go red, green, blue, and then here you go red, blue, green, and then that's the star. And okay, and then I already said that. Now also I encode the intensity of the beam that would have these properties by the intensity or the saturation of the color. Okay, so a little bit of background for Poincaré beams. And then you all know this, if you superimpose two beams that are right and left circularly polarized, then the ratio of the amplitudes determines the ellipticity of the polarization ellipse, and the phase, relative phase, determines the orientation. And so if we combine two beams in, say, Laguerre-Gauss modes, collinear, and then because Laguerre-Gauss mode, say L equals 1 and L equals 0, they have different amplitude and phase differences. Then, since one is polarized right-handed and the other one left-handed, then you're going to have different points along the beam that have different states of polarization. And then that's what gives rise to your Poincaré beam. And here you have it, that's your lemon. And then there's this index that refers to the rotation of the semi-major axis as you go around the beam. So in one turn, it rotates by half a turn. And then for the star, it rotates in the opposite direction. And then these type of beams have been measured before by a group at Rochester, ourselves, and then the group in Italy, Marucci and Cardano, and also Ibrahim Karimi. And and the group of Rochester includes Miguel Alonso and his name escapes me. Tom Brown. Yeah. And okay, so but now more generally, you can combine Laguerre-Gauss with index L1 with another one of index L2, and so then the say the rotation index for the semi-major axis of the ellipse can be really arbitrary, depends on L1 and L2. So for example, you can do L1 is 3, L2 is 1, and then you get an index of 2. You can't see this very well, but you get like a little flower pattern. In fact, Lorenzo showed that pattern today because they did a similar measurement with a Q-plate. And then we've also been doing these type of measurements and more. We've been working on making monstars. So then when this index goes above 1/2, then Freund called it hyper C points. So we're making hyper lemons and hyper stars and also hyper monstars. And then recently we've been doing this work. I'm not going to tell you much about that, but it involves a setup where you have two spatial line modulators, and you in one spatial line modulator you encode one mode, and the other one you encode another mode. Spatial line modulators encode only on a component of the electric field, so that two spatial line modulators are rotated. So you encode one mode in the horizontal component and another mode in the vertical component, and with a quarter wave plate you convert the horizontal and vertical into circular states. And but let's go to the Mobius problem. So now we want to combine these two, but now non-collinear. So we have a Laguerre-Gauss mode, and here just a fundamental mode. So collinearly, they make one of those lemons or star patterns. Now each of them has its own coordinate reference frame, but now we're going to look at some observing plane. So if you transform the fields of the two beams into that observing plane field, you're going to get, of course, a z component for both of them. And then, of course, you're going to have an x component that depends on the angle and a y component that does not depend on the angle. Okay, and so let's try this. Let's make one of these beams, Poincaré beams, but now let's start getting them off alignment, that is, making them non-collinear. So then as you start increasing the angle very slightly, so what starts to happen is that the rotation of the semi-major axis, it starts to increase by a lot along certain directions. And as you increase the angle further, you start to get polarization fringes. And so then if you analyze the polarization fringes, you start to see that as you go from here, red to red, the semi-major axis just went half a turn. And then you go again red here, it went through half a turn again. So what the polarization ellipse is doing when going through here is doing this rotation. But when you come around, it undoes that rotation, but it undoes it by one number less in this case, so that you get a net half a turn when you go completely around. And then that's going to be the origin of that Mobius strip. But we need to look one more thing there too. Now this is how we do it in the laboratory. You create two beams. They go to a spatial light modulator where you encode the modes in diffraction, and then one produces a Laguerre-Gauss mode, another one just a fundamental mode. They get combined at an angle, and then you just observe them. And but now, how do we measure this pattern? Well, we've been trying to just think of some polarization trick. Okay, we're still looking for that polarization trick. But if we put up a polarizer and look at the y component, if you might see that there's some fringes here, and then there's some other fringes here for the x component. And so for now, let's ignore that there's a z component. Let's consider just x and y. And so if we just do polarimetry, just find out what is the state of polarization at each point. And the z component is really tiny, so we could say, oh, let's say this thing is two-dimensional. And it's not exactly two-dimensional, but then you can see how these fringes start to form. So these are the polarization fringes I was mentioning. And here you have some more. And okay, so then let's get back to looking for the three-dimensional aspect. And okay, so let's think here about the electric field. When the y component of the two beams are in phase, the x components are out of phase. And conversely, when the x components are in phase, the y components are out of phase. So if we put a polarizer, vertical and horizontal, we'll see that for the vertical, we'll see, is that my ring? No. Yes. You'll see, 5 minutes. You'll see fringes, but then the fringes in the x direction are complementary to the fringes in the y direction. And now if you look at the z component, something happens with the z component that when the y components are in the same direction, the z components are also in the same direction, or also in phase. So the z fringes should be the same as the y fringes. So then that's a clue to understand this thing a little better from projective measurements. Now let's look at the z component, and we can compute the the semi-major and semi-minor axes of the ellipse. And if you, let me back up. So then if you compute the, just from knowing the total fields at each point, you compute what is the semi-major, the direction of the semi-major axis of the ellipse, you get this type of a pattern. So the z component is also turning in such a way that in this situation where you have two beams crossing, the semi-major axis of the ellipse is turning in 3 dimensions. And here I've color-coded the various twirls of the z component. So let's say from pink to blue is one crossing of the plane, and from red, from green to red is another crossing. So there's a crossing, let's say here, and then later here. Actually, wherever there's a dark fringe in the z fringes, there's a crossing of the z component of the field. Okay, and but what is peculiar is that as you go, okay, so here I was focusing on what is the semi-major axis at some circular, imaginary circular path in the plane where the two beams cross. And if you go to a different radii, you will get more turns. So in fact, the semi-major axis is twirling a lot, as more and more as we go further out from the center. And then here are some pictures in 3 dimensions. And now here we're blowing up the z component. And so I hope I can convince you that if you calculate these fields in 3 dimensions, they're going to have this pattern. If the L of the Laguerre-Gauss mode is an L equals 1 or 3, an odd number, you're going to get a Mobius strip. If it is an even L, then you're going to get a twisted ribbon. That is, that you'll get one full turn of the ribbon, and then it reconnects when you go around. Okay, and you can see there's all kinds of rich dynamics in the sense of the orientations of the polarization in 3 dimensions. And we're only looking at just one particular location. Okay, so the challenges are the experiments, because we can measure the y component, but we can, with a regular polarizer, we can only measure the sum of the x and the z component, not just the x component. Originally, our hope was to measure x and y, and from the total subtract to get z, but we can't do that. At least not with a regular polarizer. And but there's some hope. Some polarizing beam splitters don't reflect the z component in an uneven way. So we could try to play some tricks with that. So in conclusion, I'm going to tell you that non-collinear Poincare superpositions can produce 3-dimensional twists in the polarization ellipse. The simulations reveal a 3-dimensional land field that is really complex and rich. And we're still working on that experimental confirmation. And then one more slide that I want to make is this one, that in February, there's the 2016 edition of the Complex Light meeting in San Francisco. This is our 10th edition of the conference. The deadline was August 1st, but we're still accepting submissions, so I encourage you to submit for the conference. And thank you very much.
Thank you. Any other questions?
The mission cross polarization, does it give either?
What?
Cross polarization. If you keep the measure image in the cross polarization, so does it?
When you if you grab a polarizer and you turn it, it's still gonna measure the entire component along the horizontal plane.
If you polarize in the particular directions, and then you just image, then you don't.
If you have cross polarizers, nothing is going through, unfortunately.
Is there another question? Perhaps one I didn't get, if you make the radius larger and larger, why did you get more one Möbius twist? Because your singularity stays the same.
Right, but what happens is that every fringe is one twist.
Is it
So,
really a twist or only a twist forward and back? Do you know the sign of the rotation?
well, no, it keeps going. When you go on the top part, it goes in one direction, and when you go in the bottom part, it goes in the opposite direction. So you always have come down to just one half net turn or one whatever number.
If there's no more questions, let's thank them once again.
So I'm going to talk about something that will seem pretty different, but hopefully I can convince you that my work in BECs has a lot in common with what all of you are doing. So this work was done with my lab mate Justin, who is also here, and Nick Bigelow's BEC group at the University of Rochester. Nick is also here. And so we study vortices in a BEC. And so these are familiar images to you, but they're actually interfering atoms. So in the BEC community as a whole, we're interested in a lot of things. One major topic right now is quantum simulation and making analogs to phenomena that are found in other fields, specifically in condensed matter physics. And so this depicts vortices in superfluid helium in an experiment last year. But the BEC is even cleaner than a superfluid helium system because we can really engineer the wave function of the condensate precisely. And so that's what we do in our lab. So a BEC is a quantum state of matter where the de Broglie wavelength is larger than the interparticle spacing here. And so one easy way to think about it is as an atom laser. And so the BEC shares a lot of properties with lasers we all have in our labs. The most important being that they're coherent and single mode, and really they just are similar. And so one of the questions that we're asking with our research is how far we can take this analogy between BECs and laser physics. And so really some of the first experiments done with BECs were atom lasers. And so to this analogy, we add the spin state of the BEC, of the atoms. And so this is the different Zeeman sublevels, the M values within a hyperfine spin manifold in the condensate. Of course, in a laser, we all know this is the spin angular momentum of light. And then we also include the phase in describing the BEC. And so you all know that an azimuthal phase generates a vortex in an optical beam. The same thing is true in the BEC. If you have an azimuthal phase dependence, then you have a superfluid velocity, which is the gradient of that phase. And so you can make a vortex in the condensate. Okay, so these are some of the things we've been thinking about in translating ideas from singular optics into atom optics. We've heard a lot about C points, Poincare beams, a little bit about the GUI phase today. And so these are all things that we've been working on, demonstrating, measuring. And then we've also heard a little bit about cylindrical beams. I'll be focusing on these today. So this is kind of what you picture when you think of a radially polarized beam and an optical beam. And so what we want to do is engineer a radial spin distribution in the condensate that corresponds to a spin monopole. Likewise, this kind of pi radial cylindrical beam that you're all familiar with is important in BEC as it's a different type of monopole. And then we have a couple other presentations at this meeting where you'll hear about some of these other ideas. Okay, so in BEC system, we're interested in engineering spin textures. And really this is just a vector vortex equivalent. So we have spatially dependent spin states, spatially dependent phases in the condensate. And so in our BEC, we can choose either a pseudo-spin 1/2 system with 2 states populated. This would be like the 2 polarization states in an optical beam. Or we can populate 3 different states. And so this is a spin 1 system. And this 0 state here is analogous to having polarization along the z-axis, which we've also heard a bit about today. And so this spin texture describes the local spin at each point in the condensate. And again, since if we choose to have 3 states populated, the spin can rotate out of the plane. And again, we've already heard about some 3-dimensional structures in light today. So this spin texture is one example where in the center of the beam, or the center of the cloud, there's only spin up population, and along the edges, there's only spin down. And so we can control this texture really well. Okay, so how do we actually do this? We use a coherent 2-photon Raman interaction. You can really think of it as just a Rabi oscillation to transfer population between 2 spin states. And so this is this conservation of spin angular momentum changes these spin states. If we make one of these beams the Laguerre-Gauss beam, conservation of orbital angular momentum allows us to create a vortex in this final state. So this is what it looks like in the lab. We separate the spin states and image them individually. And so we end up with a vortex in this state and a non-rotating component in a different spin state in this over here. And so this looks just like what we've already seen in the past talk. 2 components, different spin states, different orbital angular momentum. We can also do matter wave interference. And again, these pictures, you might think they're from your lab, from a laser, but these are actually atoms interfering in the BEC. Okay, so one of the things that we're most interested in right now is creating topological structures in the BEC, specifically monopole structures. The ones that we're creating are sometimes called hedgehogs. They're related to the 't Hooft-Polyakov monopoles that were described 40 years ago or so to try to explain the magnetic monopole problem. Why don't we have isolated magnetic point charges? Or we haven't found any yet. And so the search for these naturally occurring magnetic monopoles continues. CERN is working on this. There's a lot of active research in this area still, despite not having any results yet. And so the lack of information here kind of motivates our desire to create these magnetic monopole analogs in systems we can control. So there's been a lot of work in solid state systems. If you just look, it's all nature science for a while. And then more recently, creating structures in BECs, and again, nature science. So these are exciting things to try to create. And so coming from a singular optics background, I see a spin monopole in a BEC paper, theory paper by this Finnish group, and of course it looks like something from singular optics. The more complicated structure that was described in this paper is a radial distribution in the vorticity of the BEC instead of in the local spin. And so this corresponds to a spin texture that looks like this, which is in superfluid helium. It's called a cross-disk gyration. But of course, we all recognize this as some type of cylindrical beam. And so the vorticity is the curl of the superfluid velocity. And so creating this type of structure in the BECs is like a synthetic monopole field. Okay, so to make this radially polarized distribution in an optical beam, one way to do it is to combine these 2 modes that are opposite circular polarization and have opposite OAM, and then have this phase shift between them as described in this paper, but I know a lot of, you also work on these types of beams. And so the way to find out how to make a radial spin texture in a BEC, you can approach it purely from the BEC physics, and that's what these Finnish theorists did, a number of other theorists. But it ends up being the exact same thing. We have a vortex in one spin state and a vortex in the other spin state with opposite helicity, and then there's a phase between them. And then so this other cylindrical vector vortex beam, the corresponding spin texture for that type of monopole, again, we can approach it from the BEC physics side, or we can kind of say, well, we know how to make this in singular optics, so let's just steal that idea. And so you can see that these, you kind of switch where the helicity of the vortices between these two configurations to get these very different spin distributions. Okay, so how do we make these things in the BEC? We start with population in this central state, the spin zero state, and we apply two beams that simultaneously transfer population out of the zero state into the +1 and -1 states. One of these beams contains an optical vortex, and so these two kind of lambda halves to this process are mirrored, and so we create opposite vortices in these two spin states. And this corresponds to radial spin texture like this. It's also important to tune the phase of these beams relative to each other, and we have good control over that as well. We can verify that these vortices are actually opposite rotation using matter wave interference again, and you can see that these guys are rotating in the opposite directions. To make an anti-monopole, we just adjust the phase between these two beams, which we do interferometrically, optically, and we can measure that atomically. I won't go into that here, but we can make a spin anti-monopole, and then we can make this other crazy vorticity monopole that corresponds to this other type of cylindrical beam. And here we just change the handedness of the beam that we're using to couple between these spin states. So using fairly old ideas from singular optics on these cylindrical beams, we can create three completely new types of spin textures in the BEC. Our next steps are to imprint multiple spin textures into the condensate and watch them evolve. Of course, atoms interact, photons, it's a little harder to get them to interact, but we're hoping to see some interesting evolution that's been predicted by a number of BEC theorists. So in summary, we can control and measure the wave function of the BEC. So far, we've been focusing on studying vortices in the BEC and relating it to all different types of physics. And we're really just getting started. We're working on building up new infrastructure to measure the evolution of these structures in the BEC. So I'd like to acknowledge helpful conversations with Alonzo and Brown, who we've already heard about today, Mishkat Bhattacharya at RIT, and then some BEC theorists elsewhere. Our entire lab is here at this conference, and we have a number of other presentations that I'd like to invite you to come talk with us. We're really here to find out the latest in singular optics and steal your ideas and apply them to our work, because vortices are everywhere, and finding these connections is a lot of fun. So thank you.
Thank you. Other questions, please?
So now these are, when you say spin one means the entire BC is forwarding?
So let's see. So the spin one that I think you're asking about is the number of states that are populated. And so within the BEC, we have up to 5 different states, and we can selectively populate those different states. If we only populate 2, we can treat it as a pseudo-spin 1/2 system, and then things like lemons and half quantum vortices become possible. If we populate 3 states, then we have a spin 1 system. We can also have a spin 2 system and create things that don't have an analogy in singular optics yet. Is that what you mean?
The whole thing is, the whole thing
It's a matter, it's rotating.
Yeah. Oh, yeah. So for this example, we have 3 different states populated. This component is not rotating. This component has 1 unit of OAM, and this has 2 units of OAM. And we can tune, if they're positive or negative, and we can create rings that don't have OAM. And is that okay? Yeah, it's rotating.
It's just a follow-up. Do you have a coherence time for these states?
Yeah, the coherence time is very long since it's a Bose-Einstein condensate, and so it's really like tens of seconds.
So I assume this is now in two dimensions. So when you want to create a real hedgehog, you have to sort of create something in the 3rd dimension, right? So do you have a way to do that?
Yeah. So our BEC is our imprinting process for now. All the structures are essentially 2-dimensional. We're working on moving towards 3-dimensional work. Some other groups, David Hall at Amherst, for example, uses a magnetic field to imprint spin textures in the condensate. So if you move a magnetic 0 Helmholtz configuration through the cloud, you can end up with a 3-dimensional hedgehog. And that's, so that's these references here. But yeah, so it's possible. We're focusing on 2-dimensional structures so we can engineer multiple ones in a condensate and then watch them evolve. There's no way to make an anti-monopole with a magnetic field, so 3-dimensionally.
So you had a last question? You're in the blue shirt. Do you have a question?
I would like to ask something about the same as the other gentleman. So it's about the 3-dimensional experiments that you said that you haven't observed.
Yes.
So, but your final goal is.
Sorry?
But you're going to try that in the future.
Yeah, so the structures that we've made are in like a 2D slice, but it is possible to make a 3-dimensional structure too. The 2 kind of imprinting methods optically that we do and magnetically that other groups do are complementary in that ours are better suited to certain types of evolution studies. Is that okay? Yeah.
So let's say I see once again. Next presentation is about vessel beam.
The organizer is thank you for the opportunity to talking about the world and the university industrial and part in Creole. The outline is an orbital angular momentum in a vessel gown beams and some applications. Second part is a theoretical analysis and numerical results. Third part and some experimental results. And 4 is a conclusion. The orbital angular momentum. This is a most typical wavefront when a orbital angular momentum. Okay, sorry. This is the most typical front when the orbital angular momentum. And the phase of the orbital angular momentum vary in the 0 and 2p. The phase is m by theta. The intensity always is a measure of 0. The typical distribution for a vessel Gauss beam is this. When the phase for a n equal 0, n equal 1, and n equal 2. This is the intensity and the typical phase. The application in the typical optical trapping and multiplexing information. In this part, it's important how is the value of the orbital angular momentum. For this reason, for the question, how can one measure the value of the ANM? The one possible is using the diffraction pattern of the vessel Gauss beam through of the rectangular and pentangular aperture, based on the working of the triangular aperture. The theoretical analysis of the complete aperture part as a considered a Bessel-Gauss beam of this four, and diffracting in the far file analyze your spectrum. Your spectrum graph is this. We indeed this is this is a it's a far file distribution pattern in a Fourier transform. This is a some numerical results. When I use diffracting the orbital angular momentum vessel when charge n 1 and -1, 2 and -2, 3 and -3, 4 and 5. In this pattern, you can say is find the value depending on the number of the spots in the darkness zones in the numerical pattern. For example, for a 1.5 one topological chair, you obtain in the far file one dark zone. For two, to obtain two dark zones. Similar for these results. When you rotate the aperture, you obtain the result rotating 2. Then now it's possible find the value of the topological set, but no it's possible determine the sign of the orbital angular momentum beam. For as you complete the square aperture, you obtain the result, but not possible design the value at the C. Una partial explanation of the what happened when these results is a start of the considering the vortex core, and it's possible to expand the vortex core in a Laguerre-Gauss orthogonal model. When the coefficient is this. If we use the zeta is 0, the Gauss phase, the Gauss transform in this distribution, when they have the intensity distribution, obtain that the no important, we change the sign is the same intensity distribution. Now, if you complete now the pentagonal aperture, you obtain when an equilateral the results. It's not possible to determine the topological chart, but if we use the no equilateral pentagonal aperture, you possible determine the design. Again, if the darkness zones is the topological set. For example, for N1 it's possible to obtain one zone, N2 two zone, N3 three zone, etc. But if you use the negative chart, the intensity pattern is rotate. They rotate opposite to the topological positive chart. But now, if we use dividing the aperture in a sides, it's the same process. It is similar process for complete aperture, and you obtain. So, if it's one bottom side left side, upside, and left side. Sorry, right side. And you possible to reconstruct the intensity pattern using the Bohr rule. In general, when you have using a rectangular aperture and you use the Bohr rule, you obtain it's possible to reconstruct the intensity pattern. It's similar when you use the pentangular aperture. It's possible reconstruct the vessel path, the far-field pattern using the Bohr rule. And the general results for a N1, N0, N2, N3, N4, and obtain the results. But if it is possible to implement into experimental setup, is using basically the collimator and LCM and create the vessel pattern and the aperture, the length for find the far field, Fourier length, and in the focal plane it's possible to obtain the far field pattern. This is the experimental result. For example, when I have a square aperture, you obtain the result. When you have a rectangular aperture, the result. And the rotate rectangular aperture, you obtain the result. In this result, it's possible to find, design, and the topological, the topological chair using the diffraction pattern. The similar way for no equilateral pattern, you obtain these results. And it's possible to find for you use the intensity, the topological chair negative, it rotate the pattern. And this is another result. In general, when you have using for this pattern, this aperture, you obtain the left figure is the theoretical, and the right figure is on the experimental. If you are, it's possible to, it's very similar to the figures and according to the results. The conclusion is it's possible numerical and experimental that the far pattern for an equilateral, non-equilateral, pentagonal aperture, although to obtain full determination of the integral topological chair of the Bessel-Gauss beam, including its sign. The diffraction pattern for a square or rectangular aperture allow to obtain only the absolute value of the integral topological chair of the Bessel-Gauss beams. If the complete far-field diffraction pattern for equilateral and equilateral aperture can be obtained use the Bohr rule. Is the acknowledgement for Colciencias, Colombia, and the University Industrial Santander. Thank you so much.
Thank you. Other questions? Perhaps I have one. Can you also use a stripe?
Sorry?
Can you also use a stripe as a diffraction pattern?
Yeah.
So you don't need to have an octagon?
No.
You can also use a stripe.
Yeah. Thank you.
Has there been another question? So let's thank the speaker once again. The last presentation is from our group, so then it's your turn to ask questions.
It works, last talk for today. As you already heard, my talk today is about the holographic generation of vectorial flower gardens and spiderwebs. So our motivation was to create a setup which can holographically modulate Poincare beams, so beams with spatially varying states of polarization, as for example our linearly polarized vector beams, as we already heard about our radial and azimuthal ones, and we could also have combinations of both. Moreover, we want to have the possibility of generating singular beams, so polarization singularities as V points, C points, or L lines. In the following, I will concentrate on the generation and also 3D analysis of our vector beams, whereby we want to have the possibility of generating variable numbers of V points, higher order V points, at arbitrary positions in our transverse plane. Okay, so our setup for the modulation looked like this. We have our dynamic polarization modulation system consisting of 2 quarter wave plates and a spatial light modulator. So our spatial light modulator is a phase-only one, which can only modulate horizontally polarized light. So we can only shift our horizontal components in phase. This means if we have, for example, elliptically polarized light, the horizontal part will be shifted and the vertical part will only be reflected. So we can introduce a phase shift between the horizontal and vertical components. So we have our green laser in the first step expanded by 2 lenses and then horizontally polarized by a half-wave plate. Then we have our first quarter-wave plate. Now, depending on the angle of the first quarter-wave plate, we can choose the ratio between horizontal and vertical components of our elliptically polarized light, which will reach the SLM. So, in the next step, our elliptically polarized light will be shifted in phase while we introduce the phase shift. And then in the next step, we have another quarter wave plate, which recombines our states of polarization. By this setup, we can now produce states of polarization which can be found on a ring on the Poincare sphere, whereby this ring, the radius of the ring, depends on the angle of the first quarter wave plate, and the position of this ring depends on the angle of the second quarter wave plate. So each state of polarization which can be found on this ring belongs to another phase shift introduced by the spatial light modulator. Okay, so if we would, for example, choose to have 45 degrees for both of our quarter wave plates, we can achieve all states of polarization which can be found on the equator of the Poincare sphere. So each of these states belong to another phase shift which we can give on our SLM. Okay, so in the following we want to generate vector beams. This means we only need these linear states, so we only need the ring on the equator. This can also be achieved by the angles 45 and minus 45 degrees. And if we now choose to have, for example, these two or one of these two holograms, we could achieve a radial distribution or the azimuthal polarized beam as in these two cases. So in these cases, it's not so good to see. I hope you can see it. We have small polarization ellipses, which are measured here in our transverse plane by a rotatable quarter wave plate and a fixed polarizer in front of a CCD camera. So we can measure our states of polarization pixel-wise. So in this case, we have now in the center of these beams our polarization singularities, our V points where the polarization is undefined. And now if we want to characterize these V points, we use our Stokes field index. So as I said, we measure our Stokes parameters pixel-wise, and now we can calculate by this the Stokes field, the complex Stokes fields, which is defined by S1 plus IS2. And for this, we can also calculate the phase as the Arcus tangents of S2 over S1. In this case of the measured radial polarized beam, we have a distribution which looks like this. And in the center, we have now some kind of phase singularity, which can be defined by our Stokes field index. So the change of the phase by surrounding the singularity in the center counterclockwise divided by 2 pi. So in this case, we have an index of +2. So now we can use this index also to characterize the vector beams we are creating. If we have higher index singularities, the structure of our vector field depends on the sign of our Stokes field index. So we can have flowers and we can have spider webs. Flowers are achieved if we have a positive index. So if we take a look at our phase distribution of the complex Stokes field, we have a positive index of +8 in this case. So we will have the shape of a flower. In this case, we have 6 petals, so sigma minus 2 petals for our flower. And here's just a flow line image. So on the other hand side, we can also have spider webs, which are achieved for negative index, as we can see in the phase distribution. And in this case, we have sigma minus 2 hyperbolic sectors in our spider web. So if we have -8, we have 10 sectors. Okay, if we now want to experimentally realize these vector fields, we use a special setting for our dynamic polarization modulation system. If we use -45 degrees for both of our quarter wave plates, the phase hologram which we are giving on the SLM is equal to the phase of the complex Stokes field which we are measuring in the transverse plane. So we can by this now directly modulate our complex Stokes field, so we can directly choose which kind of singularities we want to have. We can choose the order, position, and the shape of the vector field. So for example, we could choose to have our flower we have been talking about before. So this is the hologram we used, and this is now equal to the phase distribution of the complex Stokes field we are measuring in the transverse plane. So we have an index of +8, so we have a flower shape with 6 petals. Again, here we have our small polarization ellipses just measured. On the other hand side, we can also have our spider web. Again, phase distribution on the SLM is equal to the phase distribution of the complex Stokes field. And we could also choose to have another position for our singularity. In this case, we have some kind of a 2-petal flower, which I will name in the following spider, because it looks like a spider. And in this case, again, we have the phase distribution is equal to phi 1, 2. Okay, so we know that we can choose order and position and the shape of our fields. And because of this, we can also generate complete polarization networks. So we can choose to have an assembly of higher order vectorial singularities. We just need to take care of our sign rule. This means if we have more than one singularity in the transverse plane, neighboring singularities need to have different signs of their index. So this is an experimental example of what we measured. In this case, we have a polarization distribution including spider webs and also spiders. So 2-petal flower, this means we have here a positive index and a negative index. Again, positive, negative. This means we have some kind of a square lattice of V-points with alternating signs for the indices. So if we take a closer look at what we measured, here we have our Stokes parameters, just S1 and S2, S3 is nearly 0. So in this case, we can calculate the phase of the complex Stokes field, which is again equal to the hologram we used for the generation. And if we take a look at the complex Stokes field's phase, we can see our singularities, which are also here indicated. So we have in red our negative index singularities and in blue our positive index singularities. And in between we have just some flow lines indicating the complete polarization networks of spiders and webs. So we could also choose to have different other singularities, for example, or not singularities but orders. In this case we have a 6-petal flower and a 10-fold web. Again, we have a square lattice, and this is our measurement of the polarization distribution. And in this case, we have again the alternating signs, and we have some kind of flower gardens. Regarding the case that we don't have spiders, we have again, in this case, complete flowers. Okay, so we know that we can construct interesting structures in 2D, but we are also interested in our 3D structures. So we will take a look at the longitudinal evolution of our higher index singularities. So we know that if we have point singularities in 2D, these singularities will be line singularities in 3D, and these can also form loops and knots, and we need to take care of our singularity index conservation. Okay, so in our setup, we have our SLN image by 2 lenses on our measurement system. So the 0 plane here is our image plane of the SLM. Now this is the plane in which we are normally measuring. Now we will take a look at 2 planes before and 2 planes afterwards. So here's an example. Again, we take a look at a spider. In this case, here again, our polarization distribution. And here in the low part, we can see our phase distribution of the complex Stokes field. We have an index of +4. And in the middle, we can see the ellipticity of our vector field, which should be nearly 0 because we have a vector field, so linear states of polarization. If we now take a look before and after, we see something interesting appearing. We have an area of elliptically polarized light. So here we are near to -1 for the ellipticity. This means we have left-handed elliptical states colored in blue here in the polarization distribution before and after the 0 plane. Moreover, we can see that our polarization singularity in the zero plane is now converted into 4 singularities in before and after the zero plane. This means we don't have a V point with an index of 4 anymore. Now we have 4 singularities which are located in the elliptic area. This means we have in this case 4 C points with an index of 1. And if we go even further, we can see that the area of elliptical states increases, and also the distance between the C points increases. Moreover, we can see that the phase distribution around this elliptical area is twisted left-handed before the zero plane and right-handed after the zero plane. Okay, so we have 4 C points now just converted into 1 V point with an index of 4, and then just splitting up again into 4 C points with an index of 1. So the singularity index is conserved. More generally, we have always n C points, then we have 1 V point with an index of n, and then we have again n C points. So in the case of a flower, with a higher index, we can see that the area of elliptical states of polarization is greater in comparison to the spider due to the higher index we are having in this case. And again, we can see we have a splitting up into 8 C points because we have an index of 8 for our V point. Moreover, we know that the index for our C points in this case is positive. This means we have, in the case of a flower, splitting up into laments. Moreover, if we now take a last look at a spider as an example, a spider web, we have a negative index in this case, so we will have a splitting up into C points with also a negative index. So in this case, we have stars or monsters depending on the phase distribution around the singularities. Okay, so we can conclude that we can holographically modulate arbitrarily shaped vector fields. So we can generate high order singularities with high precision, and we can also choose to have complete polarization networks like our flower gardens and spiders and webs. And we also took a look at the longitudinal evolution, where we could see the index conservation with n C points converting into 1 V point and then just splitting up again. Just as a short outlook, we are also working on more complex flower gardens, for example, hexagonal structures, and we already took a look at the longitudinal evolution of singularities in ellipse field and not just in vector fields. Yeah, that's all. Thank you for your attention, and be free to ask questions or join the conference dinner.
Thank you. Questions, please.
I have a question. How do you define the phase for inhomogeneous polarized light?
It's not the phase, it's the phase of the complex Stokes field. So the complex phase. So we have the definition of our Stokes field as S1 plus the complex I times S2. Oh, sorry, it's too far away. There. So this is not the dynamic phase of our light field. This is the phase of this complex Stokes field.
This looks like it's the linear polarization as
Yeah.
it's not the phase.
It's not the normal phase. It's the phase of the complex Stokes field. Yeah.
Okay.
I guess if you combine different patterns in your flower gardens, I mean, you do this in the near field, so you can do anything you want.
What?
So, but what is special if your polarization lines make connected structures? Is it in propagation, or where does this come into play? Because again, in the near field you can make any structure.
Yeah,
you want,
but it's pretty much not in the near field.
It's
if you also take a look at the longitudinal evolution of these structures, you can see that the it's always a continuous change in polarization, but there are also elliptical areas appearing, so splitting up of the singularities. But normally the complete structure stays continuously, so continuous. I don't know if this answered the question.
Yes.
Okay.
Question. And then, what is the difference in the experimental situation 2D and 3D? That is, in 3D seems that you measure near field because you have the full imaging system lens, but in the 2D
We are always imaging the SLM onto our measurement system. So our zero plane is always the normal measurement plane as everybody would measure it. But now if we are shifting our measurement system, so in propagation direction, we are measuring different planes of our beam, which is propagating. So we are measuring not the image plane, but before and after, as if we would take a look at the not sharp image, something like this.
But then the polarization pattern changes with propagation. So
yes, it changed with propagation.
It's not a mode of polarization, because it's not concept of propagation.
The polarization, the total index is conserved, but not in one singularity. So you have just one singularity in the zero plane. So here you have a v-point, so one single v-point with a higher index. And if you are before or after, you don't have one v-point, you have more c-points. So splitting up, so it's not stable, the v-point itself, but the complete field is still continuous. So we don't have any distractions in there. So, yeah.
No more question. Let's thank first Aline once again and all the speakers. And I get an outcome for the rest of the evening.
I didn't fall this time. So now.